University of Colorado, who is the organizer of this summer school too, will give a lecture, two of his lectures today in the afternoon and two later on during the school. So let us welcome our speaker.
Okay. Good afternoon. Hope you had a lunch. It's very cold here, as you can see. We're trying to move to a different room, but we need to get more excited here. Move a little bit. So I want you to ask me questions at some point, interrupt me, argue with me through the matrix, whatever. Okay? But we need to be more active. Otherwise, we're going to freeze. So I have a series of talks, so I'm going to start talking about this topic of light fields. Okay. So the first thing I want to mention is some basics about wave propagation. So this is in line with what Pablo was talking earlier. Ivan also talked about some of these topics. So it's essentially the crash course in Fourier optics. So who has taken a Fourier optics class? I know Crisanti has. Oh, no, I don't know if you took it. I know you teach it. Anyone has taken Fourier optics before? Okay, so that's great. So you need this, okay? Without this, it's going to be tough. And then, so Pablo was talking today about an image is a three-dimensional scene projected into a two-dimensional plane. Well, I'm going to talk about three-dimensional light field. So essentially, we are going to talk about how we can control the light in 3 dimensions, not in 2. Okay, so as opposed to images which are 2D, we're going to talk about 3D. And then also I'm connected with Pablo's talk. He talked about space variance. Okay, so that if you have an image and you look at the image, at some points it looks different than in other points. Okay, so if you move the object, it's going to blur. The blur is going to be different. Now, volume optics is a new concept, and the idea is to make very much more space variance. Okay, so something that changes really fast. In some applications, you want things to change fast. The opposite of shifting variance, which is when the object looks the same everywhere on the field of view. Okay, so there's going to be a few equations, okay? But the idea is that you can express qualitatively the ideas I'm giving here. So the equations are good, but there are not many. So bear with me. I understand most of you are physicists, so you know that light is an electromagnetic wave. Who knows that? Yeah, okay. Now the other hand. We need to get more. Okay. And now what I'm doing here is, in free space, you can decompose the 3 components of the wave. Okay. You know electromagnetic waves. If you take the electric field, it's a vector, so you have 3 components. Now, if you have in free space, you can consider it as a scalar function. Okay. You treat every component independently. And that's based on the wave equation. Let me see if I have it here. Okay, so when you do that, you are in the realm of wave optics, okay, which is a bit more general than geometrical optics. Okay, geometrical optics is when you consider rays. Wave optics is when you consider waves, but still they are scalar. You see there's no vector there. Electromagnetic optics is when you consider the vectors. And then quantum optics is when you consider the photon nature of light. And when Ivan was showing the Jablonski diagrams, then you have the quantum optics essentially. That cannot be you cannot explain the photons essentially without with Maxwell's equation. Okay, so the basic equation that governs everything I'm going to talk today is this equation. Okay, this is the wave equation for a scalar function expressed for a time harmonic function. Okay, so for a function that changes as I to the e to the I omega t. Okay. What is the name of this equation? Dennis?
Oh, Helmholtz?
Yes, Helmholtz. And everybody knows these numbers, omega, c, n. So c is the speed of light in vacuum, omega is the frequency, n is the index of refraction of the medium, k is the wave number. Okay, and lambda is the wavelength. So I assume that everybody knows these things. Okay, we are going to have an exam at the end of this talk, so you better sit fast. Okay. That was good. So now we are going to see free space propagation. So that equation governs the propagation of waves, and this u is called a complex amplitude. Okay. What is the complex amplitude? It's a field. Okay. So it depends on x, y, z. But the real thing, there's no t. Okay. So in order to get the real thing, that we know that optics, electromagnetic waves oscillate at frequency omega, which is very high. How high is omega? Or f? In hertz. How many hertz?
Gigasecond.
Hmm?
No.
No, hertz.
Gigahertz.
How many? How fast? Kilohertz, megahertz, gigahertz, terahertz. Any idea? Guess? Is it fast? Can you see the oscillations of the optics, of the light? No, so it's pretty fast. It's faster than the eye can see, but you know, anything above 20 hertz you can see anyway. So this frequency is hundreds of terahertz. Okay, so it's pretty fast. Okay, so in this complex amplitude, you don't have the terahertz. That's a frequency, so in order to get the magnitude, you need to take the real part. That's a phasor in electrical engineering, or it's called a phasor representation. Right? So you take the real part of these times e to the I omega t. Okay, and then you get some real part of u cosine omega t. And then you have some oscillatory behavior. Okay, so this way, so this is for free space. The moment you have a boundary, you need to apply boundary conditions and match the boundary conditions on both sides. But as far as you are in free space, you can take this as the components of the electromagnetic field are not going to be coupled. Okay, so you can consider this equation for each component, Ex, Ey, Ez. Okay, so now what I'm trying to do is this. I have a laser here. Okay, and I can look at the distribution of light here in my hand, and then I want to find the distribution on the screen. This is almost a Gaussian beam, so you know it's going to keep essentially a Gaussian, but if you have some shape, it's going to change. Okay, so what I'm trying to do is, if I know the distribution in one plane, say if it was a projector there, right? If I have the distribution up there, what is the distribution here? Now, I'm doing this for monochromatic light with only one frequency. This is infrared light with many frequencies. But if I project an image, how does it propagate? So let's say I have this A, and here I have a different function. How do I find it? Okay, so I'm not going to do the derivation, but from this equation you can derive that the impulse response is this, okay? So if you put a delta function, which is a pinhole here, what is the response? What do you get here? Physicists. If you have a pinhole, what do you see afterwards? You see a spherical wave, right? So what does this mean? So a spherical wave is shown here. So you have e to the minus I k r, okay? So the faces are spherical. R is the distance from the point. And then you divide by r, y, because otherwise the energy will be increasing indefinitely, right? If you have a spherical wave and you don't have the 1 over r dependence, the energy grows as you expand. So you need to decrease the energy of the amplitude of that wave as you go far. So what I'm telling you is that this is the impulse response. You can derive this from the Helmholtz equation, but it's very natural. If you put an impulse, which is a pinhole, you see a spherical wave. That's what I say. There is an I and lambda there, which is more difficult to explain. But clearly, it's going to depend on the wavelength. And this is, the I is a phase. Okay, it's a difference in phase. It's not very important at this point. So R is the distance from the point source to the screen, to every point in the screen. Okay, so if you have the impulse response, then you can find the response here as a convolution. Okay, this is a convolution. The convolution is for the physicist, is the statement of the Huygens Principle. Who knows the Huygens Principle? H-U-Y-G-E. Okay, can you? We need to get more. What does the Huygens Principle say?
Every point in a source behaves like a source of spherical waves.
Right. Every point on the wavefront, if you have a wavefront, every point on the wavefront behaves like a secondary spherical wave. Okay? So mathematically that's a convolution. Okay? Because a convolution, you take a function and spread it, you shift it over the image, and you have that same function all over the place. That's what a convolution is. Okay, so this convolution is a mathematical operation, but it's also the Huygens Principle. So he was essentially right. He didn't know about this lambda and I factors. Okay. Okay, so now, again, what I'm going to do here, this same operation that I have here, remember, e to the minus ikr, I approximate it by x squared plus y squared. So essentially, r is, this approximation is approximating a spherical surface by a paraboloid. Okay? So instead of having a spherical surface, now I have a parabolic surface. In this approximation, things become easier because r has a square root that is difficult to carry around. So now you get rid of that square root in this situation. Okay, so this is the same thing approximated. And this is true if you propagate, or if you look at the field along some direction that is specified. And that's why it's called paraxial. Okay, it's along some axis. Let's say this is the axis. Okay, and now instead of a spherical phase factor, you have a quadratic phase factor. Okay, and here all these equations look complicated. It's just the same. It's this equation expressed with the integral. Okay, it's the convolution written explicitly. So you have the difference of coordinates, and then here you integrate on one coordinate, and then you see x, y, y, y appear here, but x0, y0 can be taken outside the integral, and so they appear here. So these are different expressions of the same thing, of that convolution. And that is all what you need to do to propagate waves in free space. It's just a convolution with a spherical wave. And here in the Fresnel diffraction integral, which is what Fresnel did for these equations, it's the approximation when you substitute the sphere for a parabola. And so if you know how to program with MATLAB, Mathematica, or C, Fortran, whatever you choose, then you can, for example, propagate a wave. So from a square aperture, this is Z, how the wave is going to look at different locations. Okay? So here you see the diffraction, and then in the far field, you just see the far field pattern. Now, if you make it along this axis, you can also calculate how the intensity changes along the axis. So if you calculate the intensity along this axis, you get something like this. Okay? So here it's very oscillatory, close to the aperture, because of the edges of the square. Okay, this is the aperture. Because of the edges, it oscillates. There is a diffraction. As you go to the far field, it declines. Okay, because it spreads. Good. So just by knowing that convolution, you can do things like this and more complicated. Now, if you go really, really fast, yes.
Can I ask on that previous picture, where is the Fresnel, like you were talking about the Fresnel approximation, where is that valid in the, only
close.
near the aperture, or is it?
Yeah, I said I normally spend like a month on this in class, but yes. So the approximation is, when can you approximate x squared plus y squared, okay, as, in fact there is another term here, 1 minus, it's a first term of the Taylor's expansion of R, okay? So you can do it as far as x squared plus y squared is much smaller than a factor that includes k and z, okay? So you can derive that from that approximation. Essentially, in practice, the rule of thumb is the angles for which you observe, okay, on this plane, the angles have to be around 15 degrees. If you go farther, it's not per accident, okay? There are many papers written about when it's valid, and surprisingly it's valid in sometimes in wider angles, but if you want to be on the safe side, 15 degrees is about right. If you go more, it's a reasonable approximation, but that becomes worse and worse. So for example, for a high numerical aperture objective, like Ivan was showing in microscopy, it's not going to work. Well, it works almost, if you do the rigorous calculation and the Fresnel approximation, they look almost the same. So it's pretty robust. And the reason is because essentially I tell you why it's so good, despite that it shouldn't be that good, in principle. You have this phase, so the error is in this phase. Now, that phase appears here in the integral, and it's very oscillatory. So if you integrate something that oscillates, it gives you 0, right? And that's why things cancel out. But to be on the safe side, it has to be per accident. Okay, so now I'm going really far. So that's called the Fraunhofer regime. And here I wrote the condition, again, when Z is much larger than essentially the size of this aperture times square times K. Okay? When this condition is applied, satisfied, you can go very far, and that integral becomes a Fourier transform. Okay? If you look at this integral, okay, who knows what a Fourier transform is? I should have asked that before. Who doesn't know? Okay, so we have markers. Okay, the short version in words, a Fourier transform is a decomposition in sines and cosines. Okay, a continuous decomposition. So we have an integral. More precisely, it's a composition in complex exponentials. Like a cosine is e to the ix minus e to the minus ix divided by 2. So those complex exponentials appear here. Okay? So you decompose in these harmonics, essentially, the Fourier analysis, and the Fourier transform is a continuous version of that. So when you take this approximation, you get this integral, which is essentially the field here, and then here, if you forget about lambda z, the rest is a two-dimensional Fourier transform. And the lambda z means that you are scaling by lambda z. So if you substitute instead of x naught divided by lambda z, but you put fx, and the same with fy, this is reads exactly like a Fourier transform. Okay, so what does it mean? It means that, let's go to the image I had before. Here, if you have the A and you go far enough, you don't see an A, you see the Fourier transform of the A. Now, the Fourier transform is complex. It has amplitude and phase. So what you see is the modulo square of the Fourier transform. You don't see the phase. Okay, so here is an example. If you have a square, the Fourier transform of the square is, which is written here, this is the function that represents the square. It's a sinc function. Okay, the sinc is a Fourier transform of a rect function like this, okay, of a constant function over an interval, you get this function. This is called the sinc. Now sinc is a sine x divided by pi x. Okay, it's a sine. This is a sine divided by x essentially. Okay. And because it's in 2 dimensions, you get the product. Okay, so it's the product of this in one direction and the product of another thing in the other. So this is the aperture here described by a square. This is a function that represents a square. This is the Fourier transform. And the far field intensity, you need to substitute fx by x naught divided by lambda z. So that's all what you need to do. Okay, now for those that know signals and systems, if you know the impulse response, you can calculate the transfer function. Okay, so who knows what the transfer function is? Okay, so the transfer function is the frequency response of a system. So if you have a system, the impulse response is if you put a pinhole, and that's what you see. Now, let's say you put the sinusoids, okay, at the input of this, okay? You have sinusoids of different frequencies, okay? So like a grid. What is going to be the response of the system? Okay, so for each sinusoid, you have a different response. And that response is called the transfer function. Okay? So, interestingly, the response in frequency is a Fourier transform of the impulse response. So here we have, again, the spherical wave, and here we have the Fourier transform of this function. So let's forget about this constant. Here we have quadratic phase. Okay, so e to the x squared plus y squared. And here we have e to the x squared plus y squared. Okay, so it's essentially, functionally, it's the same thing. Why? Well, e to the something is called an exponential, right? What is the Fourier transform of the exponential? An exponential. Okay? So it's one of those functions that the function and its Fourier transform look the same. Okay? It's just, you need to put some constants around it. Okay? But the functional form is e to the I x squared plus y squared, e to the I x squared plus y squared. Okay? So that's why this is interesting. So this is a Fourier transform. I'm going to skip this part because it requires a bit more time. But essentially, this Fourier transform, what tells you, this is going to be constant. If you take the modulo of this, okay, it's 1. Okay? What does it mean? That if you have these waves propagating, they are not going to be attenuated. Okay? Because each component in Fourier space, each harmonic is a plane wave. Who knows what a plane wave is? Good. Good. So every frequency in space corresponds to a plane of different orientation. Okay? So higher frequencies, the plane waves go to the wider angles. Lower frequencies, they go closer to the axis. So essentially, none of these plane waves is going to be attenuated. We know that if we have a plane wave in free space, it goes forever, right? There's no attenuation. Unless it's very, very high frequency, in which case we call those evanescent waves. Okay, so that high frequency, what is high is 1 over lambda. So if you have a plane wave essentially that has a frequency higher than 1 over lambda, this fx here, what is fx? This fx, if this is higher than 1 over lambda, then essentially the wave doesn't propagate, it's called evanescent wave. It only exists close to the surface. Okay, so we have the impulse response and the transfer function that defines the system. You can do just use this as to propagate the wave, or you can use this in frequency space. In frequency space it's easier because it's just multiplication. There is something called the Convolution Theorem that says that the Fourier transform of a convolution is the product of the Fourier transforms. Who has seen that? Okay. Now everybody knows because I just said. So the key is this. Let's go back. Remember my convolution at the beginning? So if I perform a Fourier transform to this, so I get the Fourier transform are normally represented with capital letters. So I'm going to have capital U equals Fourier transform of this. But I just said that the Fourier transform of the convolution is the product of the Fourier transform. So you have capital U equal capital O times F capital. Okay? So that means it's easier to do a product than a convolution. Multiplying functions is easier. So it's easier to do that in a computer, it's easier to do that if you can do it analytically. And that's why it's good to use frequency domain. Okay. Another interesting thing is that if you don't want to go far, because I say if you go far, you get a Fourier transform. But how far is far? Like we had that condition, that could be really far. In order to bring the Fourier transform closer, you can put a lens. Okay? So if you have an F, now I change the A for an F, you put a lens in the back focal plane, okay, of the lens, you get the Fourier transform. Okay? So the same thing I had at infinity, now I have it at distance F. Now F is a property of the lens, which represents the distance at which a plane wave is focused. Okay, so that's good. I'm not going to do the derivation, but that's what's written here. In this plane, F represents the Fourier transform of the function that we have here, evaluated at these values. Okay? Now, who knows the FFT, DFT? Okay, you know you can do that in MATLAB. Here, what is the difference between the MATLAB function FFT, I think it's 2, it's called FFT2, and which is a two-dimensional FFT, and this Fourier transform. What is the difference? No one? This is an analog Fourier transform. Okay, it is a continuous Fourier transform. The FFT is a way of calculating the discrete Fourier transform, right? You have all bits there. And this is a continuous, okay? So this is similar to the difference between analog electronics and digital electronics, okay? So this is not going to be exact, going to be right, because there's noise. But if you do this, and take the image, this image here with the CCD, with the camera 2 times, the two are going to look different, okay? Because there is noise in its analog. That's the beauty about digital things. Now the advantage of this is that you get this at the speed of light. You shine light and the calculation, quote unquote, is done in how much time? It's not 0. What do you think is the time it takes the light to get here to you? Huh?
F over C.
You say that's a good guess. But some light, because there is diffraction, some light is going to take oblique angles, so it could be wrong. But it's pretty fast, okay? Because, you know, this could be 10 centimeters, so it's pretty fast. Okay?
Half nanosecond.
Half?
Nanosecond.
Is it half nanosecond? I don't know. You do the math. Okay. So here is F, and there is a Fourier transform of F. This A, this O, okay? So, in principle, they look pretty different, right? So in principle, you can, if I show you this, you can say it's O, and you know, they preserve the symmetry to some extent, right? So, to all extent. So this is circular, this looks circular. Here you have like 2 different axes, right? And there you go. And the F is more like a square, so it looks more like a square. Okay. So In principle, you can look at the Fourier transform and guess what the character is, and people actually use that to do pattern recognition. Okay, so you look at this, and then you get there. If you can do it with your eye, the computer maybe can do it better. So this can be used for what is called optical signal processing. Okay, so you don't need to use a computer for this part, but then to analyze the data or something, yes. But it could save you some time. Computers are pretty fast today, so you need a good argument to use this method. Okay. During the Cold War, people used processing of this type because they didn't have strong computers. Okay, so if you had to analyze a lot, so planes should fly over the Soviet Union, that's a story at least, you never know, or satellite images. And so, how many pixels do you have in a satellite image? You have trillions of pixels. So to do Fourier transform there is more difficult, but optically, the processing could be faster. Could be doable. Sometimes even with the fast computers, things are not doable. Okay, this is so that was about how waves propagate. So essentially, if I know the wave here, I can calculate the wave anywhere. That's good. Now we know how to do it. You just program those equations in MATLAB or Mathematica, and it's essentially a convolution. Now a bit about holograms. Okay. Who has seen a hologram? Okay. I don't have one here. But I have to say, I made my first hologram in this building. So there might be some holograms in the physics department. Anyway, the idea is this. We have this complex amplitude U, okay? And that U has information about amplitude of phase and has all the information about the wave for a monochromatic coherent light. The problem is when I take a picture, I capture only the intensity, that means the modulus square of that complex amplitude, so I lose all the phase information. So in order to get that phase information, you can do the following thing. You can interfere with another wave, in this case a plane wave, which is called a reference, and record that in a photosensitive material. Okay, then you develop that. So what happened here is you change the index of refraction according to the superposition of these two waves. So now it's inside there. If you come with the same, illuminate now this thing with the same wave, you illuminated this thing here, you get back the same way you would have originally if you had this point source. Okay? So you can recover this wave, looks exactly like this wave. You can recover the wave as if the object was there, but now there's no object. Okay? You only have this hologram. So you can recover the amplitude and the phase. I didn't write the equations, but it's pretty straightforward. The key is to recover the phase. The problem is that you also get some other waves that you don't want, and you need to be careful. Don't look at the other waves. Yes. Those that saw the holograms know that you need to kind of look from the right angle. So this is fine. This company, which was in Boulder, made systems for optical storage, okay, using holograms. So it was like a disk drive, but with look at the capacity, okay, terabyte, okay, better than any DVD you can. And the idea was that recording a lot of these holograms and require a lot of technical challenges, but it worked. And they had prototypes and things like that, but they went bankrupt, so they don't exist anymore. So all the science and all the technology worked, but the business didn't work. Okay? So for those thinking about starting a company, I think that not only the science needs to be interesting, has to be a good business model. Good. So the idea here was that you have you first record data similar to the prior. So this is the reference. This is the storage medium, which in this case is a polymer. And here you put the spatial light modulator, which is something that the liquid crystals in these projectors, and project an image. And then with this reference, you record that image. And then if you want to retrieve that image, you don't need this spatial light modulator. You just illuminate and get back the same image. So instead of in a DVD, for example, you focus the light and you get 1 bit. Here you focus the light and you get a page. Okay, that's why you can store more information. Okay? For each spot, you get a page full of pixels. Okay? And then you have a camera detector right there. So this is a product, okay? But it never went to the market. Now this had a niche. It was good for storage of a lot of information. For example, a whole library. You could store it in one disk and as backup or things like that. So it did work. I don't know if they coming back. Okay, so now I want to talk about diffractive optics. How are we doing with the time? What's the time?
2:53.
2?
5 minutes.
Okay, so go for 5 more minutes, okay? 2D diffractive optics. Okay, so I show you that the hologram can generate essentially any wavefront that actually exists. Because if you can generate a wave, you can make a hologram, and then you can recover it. Okay? Now, can you recover a wave that doesn't exist? Can you make something that is in your imagination? Yes, you can. You need to do it in the computer. You know, you program these functions, and then write it down with a printer with some material. Like we can use lithography or a laser or something to write all these patterns that you compute in the computer. And then you can get any far field. Okay? So that idea was first developed by Adolf Lohmann in Germany in the end of the 60s. Okay, so 40 something years, 67. So we saw a way of recording the amplitude and phase using holography. So you essentially interfere, you put together 2 waves and a photosensitive material. This is another approach. You calculate the pattern of apertures such that if you illuminate the laser through this, you get what you want. Okay? And then you need to encode the information. Okay? You need to say, okay, for each window here, I want to have an amplitude and phase. And the amplitude is given by the size of this aperture, a window. Okay? The size of the window more tells you how much light goes through that cell. And then the location of the window, if you see they are shifted, that shift encodes the phase. Okay? So the phase is encoded in the shift, the amplitude in the size. Okay, so here you have the parameters, the width, and so on. So each cell is one sample of the wave. Now, this is the original approach, or one of the approaches. Another way is to just say, okay, here I have a device that can write pixels. Okay, I have a printer, and the printer has a resolution of 600 dpi, so you know the size of the dot. And you say, I want to generate this. You know now how to propagate waves. And you say, okay, I'm going to optimize. You have a finite number of pixels, say 2 megapixels here, okay, that you can print with your printer. And so you have a finite number of options, right? 2 megapixels, you have 2 million dots that you can put black or white. So all what you need to do is find which dot is black and which dot is white. So it's an optimization problem. in a way that here you get something, the closest thing to what you want. Okay, so that's an optimization. And that's another approach, and you can generate things like this. So, depending on your ability to fabricate things, you can make things like modulate the phase, which is essentially a surface relief, a piece of glass with a varying thickness, or an amplitude, which is a set of apertures, pixels as we were talking a minute ago. Okay. So why shifting the cell gives you the phase? Well, if you think of the hologram, this is called computer-generated hologram. If you think a plane where you come here, and let's say this part is the aperture. If you move this aperture a little bit, the phase of this plane is going to change because it's at an angle. So that encodes the phase. That's why shifting this cell encodes the phase. And you can get exact equations for that. Okay, so I'm going to stop here where I'm going to talk, starting next hour, is about not doing just in a plane, but doing it in a volume. Okay? So you say, I want a function here, and I want a function here, and I want a function here, which could be different, and you can you still do it? Well, we'll see that it's possible. Okay? So I don't know if we have coffee, but we're going to stop for 5 minutes. Yes? Okay. You didn't get the exam, the final.